So let us see what the action of the rotational part of the velocity gradient tensor is by following a similar procedure as we did for the symmetric part. So we know that in, let's focus again on 2D. Yes, so we know that in 2D, the antisymmetric part of the velocity gradient tensor, well, we must have zeros here, and we'll have only one off diagonal element. So let's call that omega and minus omega. And this omega is closely related to the vorticity in 2D up to a multiplicative factor. And that in turn is related to the angular velocity of rotation, as we shall, and we'll see why that is so. So yeah, so now that we have velocity gradient tensor, the rotational part, we'll ask again what this means for the motion of a small line element. So we know if we replace the velocity gradient tensor by simply its rotational part here, we have the following equation. And what this means, of course, is that component wise we have the following. The equation for delta x2 equal to minus omega delta x1. Yes, and the solution of this equation is quite simple really. We can write it down by inspection. That delta x1 must basically go as sine omega t. Delta x2 must behave as some multiplicative constant times sine omega. Simplicity, we let that constant be unity. You can see that the derivative of this will give you minus delta x1 and so what this means is, you see what we had proved earlier, that if I take delta x1 square plus delta x2 square, which is the magnitude of delta x vector squared, this must be equal to a constant, indeed 1 in the case of column where the constant here is unity. So this means that a line element doesn't change or doesn't change its length. So the fluid is not really being deformed as it was in the case of the symmetric action of the symmetric tensor. And indeed, if we were to look at the behavior, the x1, x2 plane of a small circular amount of fluid, this wouldn't deform, but it would simply rotate. And any line element here again wouldn't deform, it would simply rotate with an angular velocity that is related to omega. And in fact, in 2D, if one computes the vorticity, the curl of velocity, we'll get something related to omega up to a multiplicative constant depending on definition. But this will be pointing in the EZ direction. So the curl of velocity, which is the vorticity, will be related to omega times pointing in the vertical direction. So this is in 2D. In 3D, you'll have a similar behavior, except that the vorticity vector won't be aligned with the z direction, but it will be in some arbitrary three-dimensional direction. But the basic fact will remain that locally the fluid will simply be rotated like a rigid body motion due to the antisymmetric part of the velocity gradient tensor. So this discussion shows that deformation of the fluid is entirely caused by the symmetric part of the tensor. And because of that fact, that simplifies what our deviatoric stress should depend on. So because deformation only caused by E, the symmetric part of the gradient of velocity, we can say tau must be the deviatoric stress tensor, must be only a function of. So you see, we have simplified the relationship quite a bit from where we originally started, that it must be some function of relative motion. So now we can ask what is the simplest relationship that we can have. So in general, one could have a relationship that depends non-linearly on the deformation, the symmetric tensor E, or on its components. You could have higher derivatives of the velocity gradient and so on. But what we will do here is take the path that the people following Cauchy did, and which culminated in the work of Navier and Stokes, which led us to the Navier-Stokes, which gave us the Navier-Stokes equations, which is soon to celebrate its 200th birthday. And the idea was to consider the simplest possible scenario. So what we do is we consider the case, consider an isotropic fluid and a linear dependence on E. Yes, so sorry, I lost the linear dependence. So what does this mean? Well, an isotropic fluid means that the stress tensor that we get for a given velocity gradient shouldn't depend on the orientation of the fluid relative to a fixed coordinate frame. And that makes sense because the material should be the same regardless of the point of view from which I'm looking at it, regardless of the orientation of my coordinate system. It should also not. It also involves the fact that the stress should not be different in different directions of the material. Now, not all fluids, all materials are isotropic. For example, you can imagine a fluid containing a suspension of, let's say, cylindrical rods. If you have such a suspension of anisotropic particles, then the entire fluid behavior itself will be anisotropic. Why? Because let's assume that the cylindrical rods are oriented in a certain direction, let's say in the x direction. Then the response of the fluid to an imposed stress, or the stress that results from an imposed velocity gradient, will differ depending on whether the flow is taking place in the direction of these cylinders or perpendicular to these cylinders. The same is true for other properties of, for example, wood, which has a fine grained texture which has an orientation. In all these cases, the fluid will be non-isotropic, and it's a standard aspect of what we call complex fluids. But for simple fluids like water and air and honey and so on, the microstructure doesn't have a preferred orientation that can affect the stress, and so in these cases the approximation of it being perfectly isotropic is valid. So there is no preferred direction or special direction of orientation within the fluid. So for such a case, and of course assuming the linear dependence, we can linear dependence of tau on E, we can write the following general relationship. So the stress tensor is related in some fashion to symmetric velocity gradient, subsymmetric part of the velocity gradient E. And another way we can include a linear relationship is through the trace of E. Other possible ways of including a dependence on E would be, for example, to include a term dependent on the determinant of E, or other sort of invariants of E that do not change by rotating the coordinate system. But these terms will be neglected because these are nonlinear. Similarly, terms like E squared would also be eliminated because these are also nonlinear. So the simplest linear relationship which obeys isotropy is written here. And then we have to simply add a multiplicative constant. So this mu now is a constant, and 2 has been introduced as it's basically convention. So in mu here we will call is basically what we call the viscosity. And there's another constant here, lambda, in front of the trace of. But we're not yet done. This relationship is the most general form of what is known as a linear Stokesian fluid, or it's also what we call a Newtonian fluid in the literature. Yes, and this has two material constants, the viscosity and this constant lambda, both of which are independent of E. Again, in the more general case, you could have the viscosity being a function of, uh, let's say, the magnitude of the stress tensor E, obtained by taking the by summing up the squares of the components of. This is in fact what happens for power law fluids which are shear thickening or shear thinning, whose viscosity depends on the applied velocity gradient. But again, those involve nonlinear dependencies on E, which we are neglecting for the moment. Therefore, the mu here is a constant. And the same goes for lambda. However, now we can make a further simplification for incompressible fluids, which is what we will be focusing on in this course. So for incompressible fluids, as I said earlier, the trace of E, which is equal to the divergence of the velocity, is exactly 0. And therefore, for an incompressible fluid, we can write down the Newtonian or linear Stokesian constitutive relationship as simply 2 times the viscosity, also just mu times the gradient of velocity, the gradient of velocity. Now, our motivation here for including only dependency on E and not on the not on R, not on the antisymmetric part, has been motivated by appeal to physical intuition and simple arguments about the way the velocity gradient affects material line elements. However, one can do a mathematically rigorous derivation by appealing to the principle of material objectivity. This has to do with, again, the invariance of the response of a material to the manner in which it is being observed. And this is discussed extensively in more advanced texts in continuum mechanics. And such an approach would directly give you this dependency on E. So we have support for this relationship from that perspective as well. But we shan't go into that in this course, since our objective here is merely to try and better appreciate the equations that we can carry on to application. So what we should take home from the developments of this lecture is that this dependency of the stress on the symmetric part of the velocity gradient has to do with the fact that it is a symmetric part that causes the deformation of materials and gives rise therefore to stresses. Now, to get some more insight into this tensorial relation, we can consider it in the one-dimensional case. The 1D case of what's known as a linear strain rate or a linear shearing. So basically the flow we had considered earlier, where the x direction, where there's only velocity in the x direction, right? Where there's only velocity in the x direction that depends linearly on the y direction. That gamma here is the strain rate. So for such a case, we can write down the constitutive relation. So we have only one component now of the deviatoric stress, that is tau acting on the y, a plane in the y direction. The stress is pointed in the x direction or directed in the x direction, and that component is given by the viscosity times, if you apply only the first term, you get the derivative of u derivative of x component of velocity, the y direction, which is nothing but mu gamma. So you see that the stress is linearly related to the rate of strain, and this is what we are usually what is usually introduced to us as Newton's law of treatment. But remember here, even though we usually call it a law in courses, textbooks, it is not really a law. It's just a constitutive relation, and it really doesn't have the status of a law that one would ascribe to the conservation of mass and F equal to ma. But just so that you can connect it to earlier concepts, we've written it. All right. So with that, now we are in a position to revisit the Cauchy equation of motion and derive from there the Navier-Stokes. Okay, so let's do that now. So for Newtonian fluid, right, that is a linear Stokesian fluid, we have the stress tensor, which has its normal or isotropic part. Sorry, it's the part of the stress that acts normally, the pressure force. That's the deviatoric part, which we will now rewrite as twice the viscosity times the symmetric part of the velocity. So if we substitute this into the Navier-Stokes equations, right, or if I write it in the other form, it's mu times gradient of the velocity, gradient of the velocity. Right, and if I now substitute into the Cauchy equation of motion, then it will end up adding an extra term, what we had earlier seen from just the pressure forces, which is Euler's equation. What we would get is density times the material derivative of the velocity, the acceleration of a material point, is determined by the gradient, negative of the gradient of the pressure, and then we have the gravitational force as before. But now we have the additional term associated with a divergence of, so it's the viscosity times the divergence of grad V plus grad V transpose, which can be shown to be just the Laplacian del square the velocity. So this gives us our famed Navier-Stokes equations. This of course has to be supplemented along with the fact that the divergence of the velocity is 0. It arises from the continuity equation and the fact that the density. Now because the density is constant, I can write it in another form by dividing throughout by density, which has just that the material derivative of the velocity is minus the gradient of P over rho, because rho is a constant, so I can define a readjusted pressure, plus nu, which is the kinematic viscosity, times del square V, plus the acceleration due to gravity, right? Where nu is equal to mu over rho, and in fact has the units, this has the units of SI system, meter square per second. So indeed it has the same units as diffusivity of mass and the thermal diffusivity of heat. And this is what underlies the interpretation of this term due to surface forces or surface stresses as a viscous diffusion of momentum. And you can also see how that analogy would work out based on our discussion of the ideal billiard ball gas. The diffusion of molecules lead to momentum transfer, which arises in the continuum system as a stress. But really this equation holds far beyond the ideal gas. It holds for a whole variety of fluids which have complex molecular structures. But nevertheless, the view at a continuum perspective of viewing this as a sort of analog to diffusion has its use. All right, so this with this we have now derived Navier-Stokes equations along with the continuity equation, which places us now in a good foundation to begin applications and look at a whole variety of problems, the realm of transport phenomena. Before we leave though, there is one philosophical point that I think it behooves us to note at this juncture. So you would have noticed that we have arrived at the Navier-Stokes equations and at the which itself came from choosing constitutive relation, which we call the Newtonian constitutive relation, purely by a combination of intuitive reasoning, some simple mathematical arguments and thought processes, and appeals to ideas of symmetry, isotropy, and linearity of relations. So, at no point in this discussion have I appealed to an experiment or a measurement of viscosity of a fluid. Now, as it turns out, this is actually the way the Navier-Stokes equations were arrived upon at the beginning. And it is purely after the fact that we've been able to do experiments, we've been able to have devices built like viscometers and more sophisticated setups and measure the velocity, not just the overall flow rate or pressure drop, which is rather less sensitive, but the entire velocity field and visualize the flow and so on. That we've been able to obtain enough experimental information to validate the mathematical ideas that were already proposed, but that is to validate the constitutive equation. So indeed, when people developed the constitutive equation originally, it was really by appeal to their common experience of the way fluids behave. They are based on ideas of what causes fluid deformation and how stresses should respond to deformations and so on. And that's sort of this out. We've just barely kind of sketched out the thought processes involved in arriving to our equation. So the underlying message here is to realize that the general narrative about science, that scientific theories are directly based on experiment, is really not true. There are some theories that do develop in that fashion, but quite often it is theory that leads the way by elucidating concepts and by ultimately telling us what experiments to design, what quantities to measure, and so on. Especially when it comes to sophisticated, expensive experiments, one needs to have a theory to know how to design the experiment, what to measure, what to look for, and so on. Another classic example on the large scale that we witnessed of this is, of course, gravitational waves. It is such a, let's say, a weak, the signal of the phenomena is so weak, requires such massive telescopic instruments which cover the entire planet and which involve the simultaneous synchronization of huge instruments across the Earth in order to detect such a gravitational wave. So it's a phenomena that we would never have encountered experimentally in the first place if we didn't have a theory, which in this case is Einstein's general relativity. And so this is just something to keep in mind, that when you encounter a phenomena, you sometimes need to suspend thinking about the data and to start thinking about the phenomena logically based on physics and mathematics. Another reason, another way to look at this is if you go back to Euler's time, there were some amount of experimental information, but it was rather coarse because we didn't have measurement instruments to get detailed measurements of the flow field. Moreover, we had very limited understanding of the nature of flows, so we didn't yet understand that there was something called a turbulent flow and something else called a laminar flow. So even if his equations were right, for example, even if he had the Navier-Stokes, it wouldn't have matched the data of a turbulent flow, for example, because he would not be able to solve the Navier-Stokes equations, and we still cannot get an exact solution for turbulence. So until we had to await the time of having computers before we could do it. So if one had simply given up at that stage, saying that I'm not unable to match the available experimental data and therefore I must be entirely wrong, we would never have reached the position where we now have the Navier-Stokes, where we can now solve it on a computer and we can now predict a whole range of flows that troubled men like Euler and the other scientists of his time. So I think that's an important point to keep in mind from both a historical perspective and a pedagogical perspective. So anyway, now that we have the equations, in the next class we shall round off our discussion of the basic principles by quickly deriving equations for the conservation of species concentration and the energy balance equation or conservation of energy. Then we'll have a full set of governing equations laid out, which will allow us to begin the study of specific problems, to begin applying these governing equations to a whole variety of interesting problems. So with that, I thank you and I look forward to talking to you in the next lecture.